Hello everyone, this is Emil Naruto. Welcome to my channel. So yesterday we have already seen how to build a linear regression model using the scikit-learn library. So yeah, so after doing some kind of basic analysis through the pair plot from Seaborn library using Seaborn library, and we have already split our data, and then we have imported train test split function from the sklearn dot model selection library. So and then we have initiated the model. We have already looked what are all the coefficients involved in our model, all the individual coefficients, that is cylinder displacement, how much coefficients are nothing but they just explain how much does that particular variable are important in the model building process, right? So when I look at here, this is the most important column, I mean variable here, and also this is also the most important variable here, that is the car type. So these coefficients explain how important does that particular variable is important to the model. Okay, and then we have already looked at intercept, which is negative, but this is meaningless. Why? Because intercept is nothing but when all our input variables are zero, we want to know what is the value of our dependent variable. So when you don't give any kind of input variables, so how much your so how do your intercept will become minus 26.69? So this is a meaningless. So in the further series, what we can do is we'll just make this intercept zero. Why? Because if it is minus 26.69, this would be a meaningless. So we need to make this intercept as zero. Okay, and then we have looked the accuracy score here. So using the function dot score, LR is nothing but our model here. See here, this is the model which we have initiated earlier. So we for this particular model we have used dot score, LR dot score function. So using that function here, we have one minute. So using that function, we have calculated the accuracy score for our train data, which is 0.82, at approximately 83% accuracy for the training data, and this is some 84% accuracy for our test data. So the train accuracy and test accuracy should be approximately equal, okay, or the test accuracy would be greater than the train accuracy. Then we can confidently say that our model is in the right fit condition, right? So now we can also compute this score using another kind of a function called R2, I mean R square. How to do that? See, from sklearn.metrics, we need to import the R2 square here, right? R square. You can call it as R square. Okay. So when I hit shift enter here, so it has been successfully imported. Now we need to predict. Our. We need to predict. So for that, I mean, you can pass it. Let's say I need to pass here train data. Oh, sorry, this is the spelling mistake here. Okay, so now what we can do is after this we need to do this like okay, so instead of y, we need to give here our predicted variable, that is y predict train. Okay, and here we need to give that particular actual column. Okay, r2 square is nothing but it is actually calculating uh, the I mean the amount of difference between the actual and the predicted one, right? So this is nothing but y test sorry, here we are actually predicting about train, right? So we are calculating accuracy for train data. So we need to use train here itself. So if I hit shift enter, you will get the accuracy that is, see here, the same accuracy, right? Did you observe here? This is the same. And now you need to calculate that for the test also. So if you do so, what happens? Let's see. Oh, okay. So when I hit shift enter, see, this is the same accuracy above which we have got using the lr.score function, and this is also the same output which we have recently got using the r square, right? So both are the same. You can use whatever you want. So this is why I have I just want you to know something that uh, uh, give me 1 second. I'll explain. Okay. So okay. So here this is the r square, right? So r square. What is the r square here? What do you mean by the r square here? Coefficient of determinant, right? So this is nothing but the r square here. So what is the use of this r square? It is used to uh, it is used to evaluate our model health. What do you mean by that model health? So when can we say that if our model is a perfect model or a bad model? That is a, if our model is a good model or a bad, how to do, how to say that? So whenever we calculate whenever we calculate the error, residual error, or the unexplained variance between the actual, right? This is the actual one, this is the actual data, and this is the predicted data. If you calculate this, you will get some kind of a score here. This is the accuracy, let's say. Okay, and if both these squares or if both the outputs are approximately equal, or the test score is slightly greater than this train score, then you can consider it as our model is a good model. And when can we and and when can we uh, say that our model is a bad model? We can say that we can say that, for example, if we have got this particular model, you have got this score as some 82, right here, 82. And now if this particular test accuracy is, let's say, some 70 or 60, something which is lesser than the train accuracies, then you can consider it as a bad model, right? It's a sorry, it's a bad model, right? Okay, so I mean, you won't just simply rely on this particular R square. Why? Because this is not reliable. Why? Why? Because I'll explain you. See, R square is a theoretical metric. Theoretical metric, right? So it's a theoretical metric for evaluating a model. If you want to evaluate any kind of model, you can use R square, but it's a theoretical one. Why we should not use r square is The meaning of it is, for example, if we have uh, see we have this x-axis and the y-axis, right? This is the x and y axis. And also, what is the mean of x here? Mean is nothing but the central value, right? So if this is the entire x, so my mean would be this. That is the x bar here. And what is the mean of the y here? So that would be the central value of y. So this would be my y bar here. So okay, now perfect. Let's imagine. So here, for the sake of simplicity, I mean, for the sake of explainability, or I'm just considering, I only have one variable, right? I only have one independent variable and one dependent variable. So this is my independent and this is my dependent variable. Okay, let's imagine I don't have, I mean, in our data set, I didn't find any kind of relationship between independent and dependent variables. That means our independent variable is not, I mean, is failed to explain the relationship between uh, these two. So it has failed. So how can we plot them if there is no kind of a relationship between independent and dependent variable? If we plot them on a scatter plot, then it would be like this absolute cloud like structure. So if you have ever imagined the shape of a linear regression model, so what would be that model? So the shape of that model is nothing but a straight line like this, right? So this is a straight line here. So all our points will usually fall on that particular straight line or somewhere around that particular straight line. But this would be the approximate shape of a linear regression model, right? But here, when you say our independent variable is not explaining dependent variable, then the shape would be this. Okay, so there is no kind of a relationship between x and y. Okay, there is no relationship between x and y. So what is the meaning of this plot here? So what did you understand by this particular plot here? So what did you understand by this particular plot? So uh, for example, you all know very well that this I have in my previous videos I have already explained how does the correlation between the independent and the dependent variable become zero. How I mean, how does that happen? I have already explained. Because this is the positive, this quadrant having positive value, this quadrant having negative value, this quadrant having positive value, this quadrant having negative value. Okay, if you sum up all these things, what happens usually? All the plus and minuses will get cancelled. For example, see here, the plus, the positive, the negative, the positive, and the negative. So what happens? All plus minus will get cancelled each other, and you will end up having the correlation that is zero, right? So this is the thing here. Okay, when the correlation is zero, that is, I mean, well, you can call it as the Pearson's correlation coefficient, right? So for example, when I say this x is not explaining y, that is, there is no kind of correlation between x and y, right? There is no correlation between x and y. You can say r is equal to zero. What is mean by r here? R is nothing but the Pearson's correlation coefficient. I have already explained in my videos, previous videos. Kindly check that videos and come back here if you haven't watched any, right? So Pearson's correlation coefficient, the notation of that is R here. R. So if R is equal to zero, how do you understand that? So let's say if R is see here, the R has been zero. Why? Because all the plus and minuses are cancelled each other, and now we are left with only the correlation between independent and dependent variable, that is zero. Okay. So now here, I just want to ask you some question. What is the probability of, so this is a sample, right? So this is a sample. So what is the probability of occurring this sample? What is the probability of occurring this sample? If I ask this question, so how do you say here? See, here I have some kind of data. Okay, so here I have some kind of data. So the sample has been extracted from this particular data, right? So I have extracted some sample which is nothing but this particular data, right? So this data is my sample. This is my population here. Okay, this is my population, and from this population I have extracted some kind of sample. Now the correlation between x and y, that is the correlation of my sample, has become 0. So now when I ask this question, the probability of occurring this sample in this particular population is, what is the probability here? If I ask this, you can simply tell the probability of occurring this particular sample in this population is 0. Is 0. How did you say that? How did you say that it's a 0? Why? Because when you look at here, this particular sample is having the correlation 0. So there is no single chance that this particular sample is actually belonging to this data. So this sample maybe belong to some other data, maybe some other data. This sample may be belong to some other data, not this data. So that's why our probability of occurring this particular sample in this population is 0, right? So what happens? So what happens if this particular sample is not belong to this particular data, and this sample is actually belonging to some other data, then what happens? Then what happens? I'll tell you. I'm just clearing it. If you want, you can take all the screenshot here. So if I can say that sample data is not, I mean, is not belong to that particular. So if I can say that, so this particular sample data, right? So this sample data belong to some other new kind of data. So what happens here when I plot that on a graph? So it will have some other different kind of shape here. Maybe a slightly as a squashed bell curve, maybe a flattened bell curve like this here. Okay, the shape of that particular sample should be like this, and this is our x bar, this is our y bar here. It will have the positive, it will have the negative, it will have the negative, it will have the positive here, right? So our our r will be either positive or negative. Why? Because see, the data is spread along this axis, right? So our our data is actually following either in the positive quadrant, or it is actually uh, it should be the negative also, right? See here, the negative. So how can you call, for example, our r will be either uh, either positive or negative. Okay, but this particular r is actually not true. Why? Because this r has happened by chance. That means it has, I mean, it's not true. Why? Because this r is actually happened by chance. Okay, r is happened here, happened by chance. Okay, which means a statistical fluke here. So this is not a real one here. So this is not a real kind of a correlation. This is not a real correlation here, right? Okay, but how it has occurred here? This has been occurred when we again resample resample from our population. Okay, for example, this is the population here. Okay, this is the population. I'll tell you in the very simplest terms. Don't worry, you just don't get confused here, right? So, for example, see, this is the correlation plot which is having zero correlation. Okay, this is having plus or minus correlation. Okay, I'll tell you from the first here. See, this is our population, right? So, this is our population. From population, I have taken small data. Okay, this particular small data, that data is nothing but this one, right? When I plot it on a scatter plot, I'm getting the correlation that is zero. That means it is not actually having any kind of relationship between independent and independent x and dependent y variables, right? Okay, so for that, what I have done, I have taken some kind of resampling again. So I have taken some resampling again here, and now if I plot them on a scatter plot, I have got this particular shape here, right? It is having some kind of a relationship, right? So either it will have the positive correlation or it will have the negative correlation, right? So this is the thing here. But when you look at here, this particular graph, right? I'll use the colors here. This particular graph has been occurred when you have done some resampling here, right? See, this is the resample. This is the sample. And when you plot something a sample on a scatter plot, you will get like this. So this is a data which is from the taken from the sample, and this has been formed after resampling here. So you can't trust R. Why? Because the R is not real. When you done so many multiple resamples here, you will get this particular data. So R is not a real thing. This is occurred by chance. Okay, for example, let me tell just I mean just look at this. Okay, for example, I have a dice here. Okay, I have a dice. So on this particular thing, it has one, it has two, and it has three. So likewise, so if I roll a dice, I have got some, I need to get some kind of the value that is the 4 here. Okay, but I haven't get 4 here. I just only got 1. But when I again rolled the dice, I have got some 2. When I again rolled the dice, I have this time I got 4. So when I roll this dice multiple times, so the probability of getting 4 will increase. Why? Because if I use multiple chances, the probability of getting 4 will increase. So in the same way, if you resample multiple times, the probability of forming this kind of a shape from our population will get increased. So due to that, this shape has formed. So this is not the original shape. This has been formed when you resampled here. So if R square, I'll tell you, I'm just clearing it all. Okay, that is, if R is, so if R is either minus or positive, then this will automatically leads our coefficient of determinant, that is R square, will also leads to coefficient of determinant. Okay, for example, if this R is happened by chance, okay, by random sampling, if R has been happened, then this R square will also happen by chance only, right? So if R is happened by chance, then R square also will get by chance only. So R square is not a reliable term. R square is not a reliable term. Reliable to evaluate our model. Why? Because if you do random sampling over and over, the R square will be changing here, right? So it's not a random term here. For example, I have said here. I have told you that if you do random sampling, okay, if you do resampling, if you do resampling here or the random sampling here, whatever may be the term, sampling you can call it as. So if you do random sampling, R square will again will change and change. What does that mean? For example, you have some 300 rows, 9 columns, right? What if you have, and again, what if the data is 300 rows, and again, what if your column has been increased, like from 9 to it has been increased to 19 rows? Then what happens? The R square value will definitely get changed, right? R square value will definitely get increased. So we can't rely on this particular R square. Did you get that? So okay, you have come to know that R square is not a reliable term. I'm saying. So what is the reliable term here now? So instead of R square, we use something called adjusted R square. So adjusted R square is equal to, the formula is R square minus the uh, the by chance here. That is the random sampling effect. We need to minus that random sampling effect from R square. So what you will get is nothing but the adjusted R square, right? So this is the thing here. So here, if you want me to explain something about R square, so R square will get increased. R square will increase when columns are increased. Okay, for example, I have a dependent variable, right? I have a dependent variable that is miles per gallon, that is mpg. Okay, this is my dependent variable, and I want to predict this particular thing using some kind of independent variables like horsepower, hp, okay, and cylinder, and okay, using these two I need to explain, right? For example, if I have added some other thing called mm, maybe watching TV. Okay, I have added this particular column, that is watching TV. So I'm saying if I watch TV continuously for so many hours, so my MPG will increase. I'm saying this. So is it true? Is there any relation between watching TV and increasing the miles per gallon of a vehicle? No, obviously no. Why? Because that's a vehicle, right? So this is my vehicle, and it will give me some miles per gallon, that kind of a thing. Okay, but here in my home, I'm watching this TV here, right? If I watch TV by sitting just in my room, will it be increasing the miles per gallon here? No. Why? Because there is no kind of a relationship between this particular independent variable and this particular dependent variable, right? So, but when we add this particular watching TV column in our data set, again, R square will definitely increase. Why? Because it doesn't matter whether it's a good predictor or a bad predictor. It doesn't matter. R square will only increase when columns are increasing, right? So this is the reason for which we don't rely on R square. Instead of using R square, we will just use adjusted R square here, right? So I want you to know something about adjusted R square. Now I am just clearing all the drawings here. Okay, so see, so this is the case. R square doesn't bother about whether this is a good predictor or a bad predictor. It just keeps on increasing when you add any new column here, right? But unlike this, our adjusted R square will decrease, decrease if any bad variable, if any bad variable has been added. So what does that mean actually? So we are saying we have MPG, right? We need to predict this column. We need to predict this column using horsepower and cylinder and I have already added some kind of thing called watching TV. So this is a bad variable. Why? Because watching TV has no relationship with increasing miles per gallon. So what happens here? Again, what happens? So this is a bad variable, right? So if any bad variable has been added into our data set, then adjusted R square will come down, right? So I have another kind of a principle. I have a condition like the standard condition, that is adjusted R square will always be less than or equal to R square, right? Always be less than or equal to R square, but but not not greater than R square, right? This is the condition here. And adjusted R square is more reliable metric comparatively with R square, right? So this is the reason here. So this is the reason for which sklearn package doesn't consider uh, R square metric here, right? And so did you ever observe we are actually importing this from the sklearn library itself, but we need to import that specifically, right? By default, sklearn library is not actually providing the R square metric. Why? Because this is the reason: R square is not reliable, because I have already explained the reason previously, right? So that's the reason for which sklearn metrics is not actually providing us the any kind of a sheet like this, and inside this sheet, yeah, it's not providing some kind of R square and other statistical terms here. Okay, so that's the reason here. But we have another kind of a library which is nothing but the uh, stats models here. We have this particular library, that is the stats models library. This library will give you all the other statistical statistical uh, results here. So using the stats models library, you can do whatever statistical analysis you want. Okay, but in the scikit-learn library you can't do that. Why? Because they have some kind of different approach in evaluating the models here. So that's the reason here. So now I'm gonna explain uh, the linear regression model, building a linear regression model in the this what do you call stats models library. Okay. 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 So yeah. So what is the difference between the scikit-learn and the stats models library? I'll tell you. So in the scikit-learn, okay, in this, see here, I'm placing two headings, that is sklearn and the stats models here. These are the two libraries here. In the scikit-learn library, you can just I mean build linear regression model here, and you can also calculate some accuracy scores here. That's it. But uh, I mean, if you want to calculate the accuracies, sklearn is the best thing. But if you want to explain what the model is actually conveying to us, so if you want to explain the coefficients, okay, if you want to explain the coefficient parameters, so stats model, and if you want to perform some kind of a statistical analysis, which is similar in case of a R library, sorry, R programming language. So in R programming language, you will usually perform statistical analysis. So in the same way, stats models provide you all the tools for which you want to uh, perform some statistical analysis here. So this is the basic difference between the two here. So see here. So if you want to build a linear regression model in the stats models library, earlier we have already split here, right? So earlier we have split the data into some train data, X train, Y train, and X test, Y test, right? So that's the case in the scikit-learn library, sklearn. But here in the stats models library, if you want to proceed for building any linear regression algorithm or the model, you need to concatenate them. Like you need to provide the data without splitting, right? You need to provide the data to to a model without any splitting. So I'm just concatenating X train and Y train as it is. So if I hit Shift Enter, see, I have got the data which has been concatenated, right? This is the thing. So you just don't look at these particular index numbers 350, 15, and you'll get confused. No matter whatever maybe the location is. For example, here, see, see when you look at here, here the data has been stored like 350, 59, and 1, and 12, and something like this. No matter whatever may be the position of the row is, but you need to understand whether all the rows and all the columns has been present or not. Okay, so you just need to understand for that. No matter whatever may be the position is, this 350 may come, can be placed here. This 59 can be placed here. This 12 can be placed there. So whatever may be the position is, you need to know whether all my rows are present in our data or not. So let's check. See here, when you combine the data, that is when you concatenate the data, you have got the stats. I mean, you have got the data as is having 278 rows and 8 columns of the training data, which is absolutely true. And where is that another column? That is our dependent column, right? So it would not be. I mean, it won't be considered here. To get that. Oh, sorry, sorry. Actually, yeah, this is a training data, right? So in the training data, we have what we have done here earlier. See, we have splitted the train data with 70% and the test data with 30%, right? So the 70% of the data is here already. 278 comma 8 columns. See, when you observe the columns here, 1, 2, 3, 4, 5, 6, 7, 8. So it's absolutely fine here, right? So that's the thing here. Uh, okay, so now what you can do is you need to initiate the model. So how to do that? First of all, we need to import stats models function, SMF, right? Stats models function. So for that, uh, import stats models dot formula dot API as SMF. So here I'm creating another variable, that is lm1, and I'm using this SMF function, SMF dot OLS function. Inside the formula, I'm passing my dependent variable first. What is my dependent variable out of all the entire dataset? MPG is my dependent variable. So I'm passing it as MPG. This is the tilde function. So So this is to separate between this is to separate all the independent variables and the dependent variables here. So this tilde function is placed between the dependent and independent variables. So this is my dependent. So I have placed a tilde function, tilde symbol here. Okay, and these are all my independent variables. Here, plus sign has no algebra. I mean, no what you can call arithmetic value here, right? So the plus is nothing but to plus is not to mean to add all the variables here. So plus is nothing but I'm saying I'm providing all my independent variables together, right? So for that, I'm representing all the independent variables in between the plus signs here, right? And I'm passing my data, which is nothing but this particular data, right? So here I have created stats underscore LR. So inside the data, I have passed this. So I want to fit this entire data to my algorithm, and I want to know whether what are the best parameters here. So hit shift enter. See, I have got the parameters here. That is, my intercept is minus 26.693, which is similar to this particular intercept, right? So, while performing the machine learning linear regression model in scikit-learn, here we have got the intercept that is minus 26.69. The same we have got here when we run stats models, and all the coefficients are the same. See here, all the coefficients are the same: 1.863, 1.863. Car type is 6.62. Car type is 6.62, right? So all the coefficients and all the intercepts are absolutely the same. Okay. Okay. So now what we can do is we can just plot the summary here by using summary function, lm1 dot summary function. If you plot this, you will get all the statistical information that is present inside this particular stats models library. Okay, this is by the name OLS regression results. Here you will get to know that this is an R squared and this is the adjusted R square. When you observe here, adjusted R square will always be less than or equal to R square, but not be same as but should not be same as R square. See, the R square is 0.826 and here the adjusted R square is 0.821. So the both are not same, right? And this is the Fisher statistic. F statistic means Fisher statistic, probability of Fisher statistic, and log likelihood. These are all the metrics with which we can decide whether our model is a good model or a poor model, right? So here we need to think whether this model is worth deployed in the production or not. We need to think here. This decision is actually taken based on the accuracy as well as other statistical tests here, right? So, but before that, I just want you to understand something. See here we have got all the coefficients values, all the standard errors, all the t's, all the p values, right? So based on this, we can decide whatever maybe the value is, right? So here at this particular position, we need to understand whether our model, okay, is this model worthy by deploying into the production environment or not. So how to decide that whether this model is worthy deploying in production environment or not. So how to do that? So for that you can rely upon the accuracy scores, right? Like adjusted R square or something, right? And also other statistical analysis like p values here, right? So you need to you can rely upon these p values here, also the coefficients and all the other things. Okay, so and one thing I want to know, what if the correlation or what if the relation between independent and dependent variable have some statistical fluctuations by chance because of random sampling? If coefficients for acceleration here is So how to do that? I mean, uh, I'll tell you. Sure. Okay. Coefficient for the acceleration. See here, 0.017, right? So this is saying for 1 unit of acceleration, our mpg, miles per gallon, will be plus or minus, sorry, will be increasing by 0.0117 times, right? See, observe here this value. So it's saying for 1 unit increase of for 1 unit increase of acceleration will cause a 0.117 times increase of mpg. It's saying this, right? So if we collect more data from the universe, we find relationship between the independent and dependent variables is zero. See, it's saying some kind of increase, right? So this is not approximate. I mean, this is not absolutely zero, right? See, the coefficient is not absolutely zero. This there is having some kind of value here. So how to do that? So we have a data. Okay, we have considered some kind of sampling here. So that sample data is this particular thing. So when you collect more data from the universe, you find relation between the reason of this particular value is there is some kind of data is missing actually. So there is some kind of factors are actually missing. So if you collect more data from the universe, then you will find that the relation between the independent and dependent variables is zero, right? So we use hypothesis testing here to find that, right? So, okay, I'll explain that part of hypothesis testing in the later video. For now, just have a look at the other thing here in the implementation part. So, okay, you have already calculated the r square and adjusted r square here. So you need to calculate some kind of mean squared error. So how to calculate that? Mean squared error is nothing but np dot mean of, you can use mean function, and inside that you need to provide the squared error, right? What is the error here? Error is nothing but the difference between the uh, actual predicted value and the actual value. And if I place two double hashtag symbols, that doesn't that means the square here, right? So square to the power of 2. So if I hit shift enter, what happens? Let's see. Okay, so it has been successfully executed. Now I just need to import the math here, and from math I need to use the square root function here. If I do so, I'm getting some value of 3.05 for my mean squared error. Okay, it is saying the distance, the difference between my actual data, and the sorry, the difference between my predicted data and the actual data is some 3.05, right? So it's actually showing us like that. So you need to obtain scores here. So how to do that? Using the score here. lr dot score. Okay, if you use lr dot score, you will get x test comma y test here. Okay, so but here one thing like okay, so here this is not the lr here, maybe lm1 here. If I do so, sorry, ls results has no attribute score here. Okay. mm, mm, maybe model as well. Okay, okay. There is a model here. Hmm. Oh, okay. Mm, okay. So yeah, this is the correct LR. Right. So yes, you have got the accuracies here. Now what we can do is we can just plot it on the scatter plot here. See, what I have done is I have just calculated the MSE, mean squared error here, between the predicted value and the actual value. So you have got the value that is 3.05. It is actually saying that there is a 3.05 difference between the predicted and the actual data. Right. So if you use this LR dot score, what you will get is this is the accuracy. And if you use this particular thing, that is you are actually predicting the value here, and if you want to plot it on the scatter plot here, you will get the shape of that our model. See, this is the shape of a model. See, this is not a perfect straight line kind of a relationship here. There is some kind of a scatter in between the points here, right? There is some kind of scatter in between the points. So this is the plot between the actual and the predicted y here. So what you can what you can see here is the relationship is a strong positive relationship, but still there is some spread, right? That's not an ideal situation. Why? Because in real world you will never get a straight line, right? So that's only for the uh, classroom kind of point of view, right? So if you want to understand better, so what we will do is we will just represent this entire thing with the help of a straight line. But that's a theoretical kind of a situation. But in practical world, you will never get a straight line here. You will always be having some kind of spread in your data. That spread is nothing but the noise here. So what is that noise? The noise is also can be called as the unexplained variance or the residual error also, right? Okay. So now how to improve? We have got the accuracy that is 0.84, and how to improve that, right? So the independent attributes have different units, right? For example, when you look at here, cylinder will have some kind of units, displacement will have some kind of units, horsepower will have different units, acceleration will have different units, year will have different units. So for all the units, if we consider all the units here, we have got some accuracy that is 0.84. But what if we scale the data? Does that lead to improve in accuracy or what? Let's have a look. So how to do that? This is a kind of third iteration, let's say iteration 3. So what is the first iteration here? That is using scikit-learn library, and this is stats models library. And now this is the iteration number 3, which is using the scipy.stats scientific python dot stats. Using this library, I'm importing z-score, right? So here, this is the z-score here. What is meant by z-score here? I'll tell you, but just for now, look at here. I want to scale the data. So for that, I'm applying z-score here, right? So I want to apply it on my train data as well as on my test data. So if I hit shift enter, okay. So now what you can do, you can initiate the linear regression model here. So like this, I'm initiating the linear regression model here, and I'm passing my scaled train data and scaled dependent data, dependent variable. So you have the output, which is our model has been initiated. And now you want to look for coefficient. So for that I'm just running a small for loop for the index and the column here and enumerate function. I'm passing the trained scaled data, and for all the columns of the trained scaled data, I want to print the coefficient for each column and the value here, right? This will be the column and this will be the value here. For that I'm using format function. So I'm passing the column here. The column will get placed here in this bracket, and the coefficients value will placed in this bracket. So if I hit shift enter, what happens? See, I have got all the coefficients here. But this time when you compare, just look at this displacement here, 0.1305, right? When you go here up here, the displacement is 0.010, right? But here slightly the displacement has been improved here, right? And when you look at the coefficient for the cycle 0.395, just have a look at here. See here 0.395. Here earlier we have 1.86, right? But there we have 0.86. And when you look at the horsepower here, minus 0.09039. But here minus 0.187 instead of minus 0.039, right? So what you get to know is the coefficients will definitely get changed when you apply the z-score technique here, right? But let's find about the accuracies also. But before that, just find about the intercept also. So, but before hitting shift enter, I want to take you to the intercept here. So let's have a look at here. Minus 26.69, right? The intercept earlier. But what happens if I hit shift enter now? The intercept value will be minus 2.85 into e to the power of minus 18. So it is approximately equal to 0 here. So earlier our intercept value in the scikit-learn and the stats models libraries also will be minus 26 point something 69 or something. But here you have got the intercept as approximately 0.0.00 something, right? So here the intercept has been reduced to 0. This is the finding, important finding. But here earlier the coefficients are having some value in the scikit-learn, in the stats models, but here the coefficient value has been changed, right? So this is the finding here. I'm erasing all this, and now after finding the intercept you can find out the score. See, the score is nothing but I'm providing the test scaled data and the uh, I mean the dependent scaled data, right? So I'm getting the accuracy 0.84, which is the same here. See, the accuracy also 0.84. This and this are absolutely the same. Do you get that? And now I want to calculate the MSE, mean squared error. So this is the mean squared error using the predicted. Mean squared error is nothing but the difference between the predicted and the actual here. Okay. See here. This time we have got the MSE2, which that is 0.3923, right? But earlier we have got what we have got here, MSE, that is 3.05. There is some kind of a decrease in decreasement in the MSE value, right? Which is a good thing. And now, if you want to predict on data here, what you can do is you just need to perform predict on our test scaled data. Okay, so if you want to plot it over scatter plot. So if you plot it, the shape would be almost the similar, approximate, yeah, almost the similar. See here, the place is almost the similar. But did you find any kind of difference here? Do you find the difference here? I'll tell you the difference. When you look at this particular x-axis, it is starting from 0, 1, 2, 3, minus 1, minus 2, right? And the data has been started from here, right? But when you move here, just look at here. The data is not same like this. Here it is having the data is starting from 5, 10, 15, 20, 25, 30, 35, 40, 45, right? Earlier, right? But after centering the data, that is after applying z-score, the data, the x data points has come down to center towards 0, right? So how does that happen? That's simple, very much simple. I'll explain. Okay. So for example, I have the x-axis here. I have my x-axis here and I have my y-axis here. Okay. Here earlier I have data some 5, 10, 15, 20, 25. Okay. 25 like this. Okay. And this is some other y data. Okay. Just ignore about that. Earlier I have some kind of relationship like this, right? So this is the shape here. Now what I have done is I have just applied z-score here. So what is the formula of the z-score? Z-score equal to xi minus x bar by sigma. That is the standard deviation. So what is the standard deviation here? Standard deviation is phi, right? So the difference between each point is phi. So how to calculate the z-score here? For example, let's imagine xi. So what is the xi here? This is the phi here. Okay. And what is the mean here? What is the mean term here? You need to calculate all these things, right? So for example, 5 plus 10 is 15, 15 plus 15 is 30, 30 plus 20 is 50, 50 plus 25 is 75. So 75 divided by, you need to calculate all the items, 1, 2, 3, 4, 5. 5 ones are 5, 5 2, 5 is 5, 5 5 is a 15. Okay, so the 15 will be the mean here. So I'm representing this digit, that is 15, is my x bar, and this is my y bar here, right? So calculate z score right now. So xi, what is the xi here? First, when we take this value, xi is 5. Okay, 5 minus what is the x bar here? 15 divided by what is the standard deviation here? Standard deviation is we have already know that the difference between 5 to 10, 10 to 15 is nothing but the sigma equal to 5, right? So write down 5 here. So what is it? 5 minus 15 is nothing but minus 10 divided by 5. If you cancel this 2, you will get the value 2, right? So what is the 2 here? Minus 2. Why? Because here it's having minus sign, right? So this is the minus 2. That's why the minus 2 has come like here, right? So now I can calculate the thing. Now let's take here this thing, 10. So xi would be 10 minus x bar would be 15 and sigma would be 5. If you calculate this, minus 5 by 5, which is minus 1, right? So this minus 1 has come like this. So likewise, the data has been centered like this. Okay, I'll tell you another thing. Okay, so now let's take here 15. So xi would be 15, x bar would be 15, sigma would be 5. So what is 0 by anything will be 0. So 0 has come like this. So likewise, we have centered our entire data towards the 0 here. So everything that are present right side are starting from 0, 1, 2, 3. Everything that are left to the 0 are starting from minus 1, minus 2 and so on. Okay. So if you do so, what happens is, uh, our intercept will becoming 0. Okay. Why? Because how our intercept will become 0? I'll explain that. For that, I'm just clearing all the drawings here. See, usually when we build any kind of model, the condition would be that particular model will always be passing, like the linear regression model will always be passing from this center. Sorry, from the center of the point where x bar and y bar are actually meeting. Okay, so this is our best fit line. This is our best fit line. Okay, now when we have centered our entire data at 0, what happens? Our intercept will become 0. Intercept will become 0. How do we know that? See here. See, the intercept will has already become 0 here, right? This is approximately 0. Why? Because e to the power of minus 18 is there. That is 0.0000 something. Okay. So this is 0. When the intercept has become 0, so see, when the intercept has become 0, that is uh, this this point, that is the entire data has been centered towards 0, then what happens? The best fit line that is passing through this particular 0 point is always be 0, right? So likewise, So likewise, our data, did you get that? Our intercept has already become 0. Okay. And then if the best fit line is passing through that 0 point, why? Because here the data is 0, then this point will always be 0. If our best fit line is passing through that 0 point, then our intercept will always become 0, right? Did you get that? So this is the thing here. Our data has been centered towards 0, and when that particular line is actually passing through that 0 centered line, which is a mean will be 0 here, then automatically our intercept will always be 0 here. So that's the thing here. So I'm clearing all the drawings here right now. Okay, let's back here. Okay, so this is the thing. But what is the reason for the spread here? The spread is due to the multicollinearity. So how to encounter that multicollinearity here? So this spread is due to the reason that the data has some kind of multicollinearity between independent variables each other. That is, I'll tell you, our independent variables are HP, acceleration, year, weight, and displacement, cylinder, and so on, right? So for example, if I found HP and acceleration are actually having multicollinearity. So what does that mean? If I plot a graph between these two, like my x-axis is HP and my acceleration is my y plot, right? If I plot a graph, so the relation should be like this. That means if HP is increasing, acceleration is also increasing, right? So you can find that there is some kind of collinearity here. So how to detect the collinearity? So using the techniques called PCA, you can detect, or you can just ignore the collinearity also, right? So we can also have another metric called VIF, that is variance inflation factor. So using PCA you can uh, detect that. Using VIF also you can detect that. So I'm gonna use this VIF technique right now, for which I'll be detecting the multicollinearity that is present in my data. So how to import that? VIF here, variance inflation factor. So from stats models.stats.outliers influence, we can import variance inflation factor. When I hit shift enter, see here, I'm saying I'm using this variance inflation factor function. Inside that I'm passing my values of my data. Okay, and then I'm saying some index, right? So for each of the index in the range, that is x dot shape here, what happens if I hit shift enter? Now I'll be I'll be running some small for loop here. That is I equal to kept 0 initially. And for each column in the x dot columns here, x is nothing but our data. Okay. So if I is less than 11, so what happens? It will go to the print function and it will execute the column and the arrow mark here. This is the symbol string, and for each of the column it will calculate the VIF here, and then again the column will get added, that is the column will get incremented here, that is I plus 1. So it will get to the first column. After 0th column it will go to the first column, and then again second column, third column, fourth column, fifth column, likewise it will go till 11 here. Okay, if it is exceeding 11, right? For example, if it is equal to 11, so the column will be 11, then it will automatically gets out from the loop. See here, when we test for the multicollinearity here, I have clearly found that cylinder is having highest number of multicollinearity 172, and then year is having highest multicollinearity, then weight, and then horsepower, and then displacement, and then horsepower, all these things here. Okay, so after finding multicollinearity, so what is this multicollinearity is indicating? Actually, when VIF is equal to 1, it indicates there is no correlation between the dependent and independent variables, right? See, when VIF is equal to 1, is there any value of 1 here? No. Why? Because there is some kind of collinearity here. So, but VIF, when VIF is between 1 and 5, then it's having moderate collinearity. Okay. If VIF is having greater than 5, then it's having severe collinearity. But when you look at here, all the independent columns are actually having VIF which is greater than 5. So by this you can say these are severely having multicollinearity. So you will have to do two kind of things here. Okay. For example, if you are building your model only to compare the accuracies, okay, only to compare the accuracies, you can just use a R square metric, R square score metric, or you can use the LR dot score metric. You can just compare the accuracies, that is 82%, the 84% accuracy score. You can just compare them. Why? Because having multicollinearity in the data won't impact our accuracies. It will only reduce the explainability of the model. That means it will only impact the coefficients here. Okay, if you want to explain the model, then collinearity is a serious issue. So you need to either remove either remove the either remove the columns here which is having VIF greater than 5. Okay, you can remove them, or you can just ignore them and you can focus on the accuracies here, right? So these are the two things which we can perform when our data is having severe collinearity. Okay, so that's all for now. Okay, I think I hope you have got a good understanding about the linear regression. So today I have already explained enough, and tomorrow I'll be explaining the hypothesis testing topic. And I just want to talk a little bit more about the collinearity also. Okay, so okay, that's all for this. I'll see you in the next video. Okay, bye and take care. Yeah, take care. Jai Hind.